So, to start, we need to clarify that the order of the switches go as follows. From 1 to 3 of the first switch is the number conformed by A0 to A2 respectively. The first pin of the second switch is the carry in that will allow us to select if an addition or a subtraction is done by the circuit. The pins 4 to 7 of the same second switch is the second number conformed by B0 to B2. The let's order is as follows. The one in the top is the first 4-bit binary digit seen from left to right. The one below is the second one, and so on. First, the subtraction of 6 minus 3 is done, which results in a positive 3, showed in the LEDs as 0011. Then the subtraction of 6 minus 4 is performed, showing a result of a positive 2, that in the LEDs is as 0010. So as A is bigger than B, the A2's complement of the result is not done, because the subtraction will always be positive. Now, when the subtraction of 6 minus 7 is done, the result is minus 1. Here the 2's complement is done in order to show a 2's complement result, which in the LEDs is seen as 1111.
So for the second part of our circuit, we've got 4 ICs and a set of 2 dip switches. The first IC is the comparator, the second IC is an AND, the third one is an XOR, and the final one is the adder. So for the first section of the circuit, we are only going to use the comparator and the inputs. These inputs work as the very first ones that go directly towards the first full adder, but since we got the problem that only one of our adders work, we are trying them separately. So for the first part, we've got the comparator, which this LED will tell us is if B is greater than A. Our A inputs are from 1 to 3 of this dip switch, and our B inputs are from 4 to 6 of this dip switch. Oops. So for the first one, if we turn on A1 on B, we've got that it is greater than A. If we equal the number with the A, we've got it turned on. That means it's not equal. It's not B. Is not greater than A. And as well, if we turn A to 3 or A to 7, if we try turning B to 3, it's gonna light up again. And as well, if we try a 7 or any other number, that it's not 1 or 0. For the second part of our circuit is important since it'll indicate if the first full adder is subtracting. We've got the second LED indicator. Well, it's not if it's not subtracting, but rather if the output will be a negative number. So we decided to use that LED to indicate us a sign on the output. So if we have B greater than A, and if the first full adder's function will be of subtraction, that means the carrying is on 1, then that LED will light up, indicating that the final result will be negative. The LED on high means that it's negative, and on low it means that it's a positive number. So for the third part, we've got a 2's complement with this full adder. We've got the LEDs organized from output 0 through output 3, being the MSB. So for this, we've got a manual full adder that will help us demonstrate that it's actually making the 2's complement. So if we decide to subtract 7, oh no, minus 7, minus 1, no, minus, well, 1 positive, minus 7, that gives us that B is greater than A, and that the output will be a negative number. So if our full adder is working correctly, the first one, it will give us an output of 1010. And what the circuit makes, it makes a 2 complement, and we can see that 1010, if you make the 2's complement, is equal to A6. So, and that works if we turn off the carry in, then we'll get 1010 on the inputs of our manual full adder. So that means turning on and turning off of the carry in will make the full adder turn the 2's complement. We can give another example of 6 minus 2. So 6, well, 2 positive minus 6. We've got 6, and we've got 2. Oops. So 6 is greater than 2, and we've got the carrying turned on, so we'll get a negative number. The output should be 1100, which in 2's complement is equal to A4. We can show this by turning on the carry in. Boop, boop. And that's our circuit board.
Well, teacher, in the third part of this circuit, we made a BC converter, and the output was a 7-segment display. The display result was an add-on, and this is the reason that we have to use a 3447 BC integrate circuit. You can put the 0 to 15. Well, when you wish the input is 10 and you wish the output was 10, the BCD need to add 6 bits, and this can be possible using an 8 and OR gate. The final of this video show how the circuit works and demonstrate that the decimal was the left and the segment was a unity. Regards, teacher.